All right, now we're going to switch to a different topic, the idea of fluid force. When you fill a tank with certain kind of fluid, we were doing integrals where we were calculating the work to pump out the fluid, but the fluid itself exerts a force on a wall that's holding it back. So let's look at an example. Here's an aquarium that is 4 feet tall, 2 feet wide, 7 feet long, filled with water. We know the weight density of water is 62.4 pounds per cubic foot. And let's start by finding the fluid force that acts on the bottom of the tank. Okay, and at the bottom of the tank, every point at the bottom of the tank is 4 feet below the surface of the water, which means every point on the bottom of the tank is feeling the force of 4 feet of water above it. Okay, and so fluid force is defined to be, you want to take the density of water, or density of whatever fluid you're talking about. Okay, this is weight density is what that W means, times the depth, and then times that by the area that it's acting on. Okay, and I like to think about units here to help me work this out. So my fluid weight density is 62.4 pounds per cubic feet. The depth of every point on the bottom is 4 feet, and the area would be the cross-sectional area of the bottom. That would be 2 feet by 7 feet, so that is 14 square feet. And notice feet times square feet is cubic feet, which would cancel out the cubic feet here in the denominator, which would leave me with just pounds. And so we get an answer of about 3,494 pounds of force acting on the bottom of the tank. That's quite a bit of force. Now let's talk about the fluid force on the long side of the tank. And what's different here than on the bottom is the long side of the tank. Let me slide this back up for a second. We have to think about is, so we're talking about the front side here. Water that is acting on the side up here is not exerting much force because it's not very deep. But the deeper we go, right, a point on the wall right around here has much more force on it because it's a function of the depth. Okay, if you've ever gone swimming in a pool, you may have had the experience, if you dive really deep, your ears, you feel that pressure of water on your ears. And that's because it's a function of how deep you are. So what the difference is here on the long side, the vertical side right here, is the depth is variable, right? On the bottom, every point on the bottom was at the same depth of 4 feet, but here we have to consider every single depth here. And because of that, because force depends on depth, and we have different depths on that side, we're going to need to use an integral, and we're going to consider thin horizontal strips at the same depth. Okay, so that's going to look like this. Let's just move this out. There we go. And just like with the work integrals, you need to make up your coordinate system. And just like with the work integrals, I usually, because I'm measuring how deep my horizontal strip is, I'm going to start with y equals 0 at the top and measure positively downward. So the bottom of the tank would be at y equals 4, and my random horizontal cross section at the same depth would be at y equals y. Fluid force is density times depth, and then this time what I would do is multiply by the area of that thin strip, and we're going to consider all the thin strips at different depths, which means we're going to integrate this throughout the whole length of that side. So depth is y feet. The area of this thin strip, well, it is 7 feet long, and it has an infinitely thin thickness of dy, and that would be in square feet. Then if I want to find the total force, then I would integrate this from 0 to 4, this formula right here. 62.4 and the 7 can come out of the integral, and you just have to integrate y, which is y squared over 2. And if you plug in 4 minus 0, you're going to get 16 over 2 is 8. Now, after I worked this out, I kind of took a second look here. It actually comes out to be exactly the same as the force on the bottom, but don't let that mislead you. That's just a coincidence with the particular dimensions I chose. One other note, part of the formula for fluid force, the first two terms, you multiply density times depth, and that is another physics idea. That gives you pressure. If you take, for example, 62.4 pounds per cubic foot times 2 feet deep, that means if you're 2 feet below the surface of the water, you're going to be experiencing 124.8 pounds per square feet of pressure. Each square foot would have 124.8 pounds of force acting on it. Okay. So you'll probably see that term pressure on there. All right, when I think of force acting on walls, what I think of is a dam, right? Especially if you're an engineering major, you might be building a dam whose job it is to hold back a bunch of water. So let's say this is a very small dam with these dimensions, 12 feet at the top, 4 feet at the bottom, and these two sides are both 5 feet. It's a trapezoid, and it's filled with water to the top. So we want to calculate the total fluid force. What I did was worked out some numbers. You're going to want to know this right here. So if you do a little Pythagorean theorem, if this is 4 and this is 5, this will end up being 3. And then like the last one, we want to consider thin horizontal strips at the same depth. And we're going to calculate the fluid force on that thin horizontal strip, and we're going to integrate all of the horizontal strips throughout the height of the dam. Coordinate system's the same. I have y equals 0 at the top. Y equals y is where my random strip is, and the bottom would correspond to y equals 3. Now the length of, well, let's get to the formula. Force is density times depth, so I have 62.4 times a depth of y feet. Then I want to multiply by the area of this thin strip. So we need to break that up. This part right here is 4 feet long, and by symmetry, I could call these other two end pieces x feet long temporarily. So my area is 4 plus 2x times the thickness, which would be a small increment of y. Now, how do I get x in terms of y? We're going to use our old similar triangles trick here. Let me see if I can squeeze that in there. Yeah. So remember how that works. If you think of this smaller triangle is similar to the bigger triangle. So x corresponds to 4. X is to 4. Has to be in the same proportion as this length on the small triangle. 3 minus y is to the total length on the bigger triangle, which is 3. And then I just multiplied by 4 to get x by itself, 4/3 times 3 minus y. And total force is all of that multiplied together. I took out the 62.4. Integral would go from 0 to 3. Y times 4 plus 2, and this was my x that I solved for here, dy. All right. One more. It's kind of an interesting one. The other thing I think about when I think of fluid force, you think about like a submarine, for example, that goes below the ocean at very deep depths, actually, and a lot of submarines will have little circular windows on the side of them, and they actually experience a tremendous amount of fluid force on them as they dive deep below the ocean. This will give us a sense here. So let's say I have a circular window, 1 foot radius, and I'm not drawing this to scale, but let's say we're submerged 100 feet below the water. And by 100 feet, I mean the bottom of the window is 100 feet below the surface of the water. How much fluid force is acting just on that circular window? Okay, so we draw a nice picture. As we've seen with some work problems, it's nice if you have circles to let y equals 0 correspond to the center of the circle. And I'm going to measure y downward to this thin horizontal strip that's at the same depth here. Okay. Yeah. So fluid force, density times depth. Now, the depth would be, the depth of this strip is y feet, right? This distance plus, remember, this bottom is 100 feet below. So if this is 1 foot, there would be 99 feet of water above the center of the window. So my depth of this horizontal strip is 99 feet plus y plus 99, times the area of that thin strip. I broke it down into calling this piece x, and by symmetry that would be x. Once again, by adding that extra radius in of the window, I can use a Pythagorean theorem to solve for x as the square root of 1 minus y squared. So I'd have 2x times dy as the area of my thin strip. Plug that in. And my total force, oh yeah, be a little bit careful here. In terms of y, if y is equal to 0 here and I'm measuring y positive and I want to capture this entire window, right, all of the horizontal strips, then my lowest strip here is at y equals 1, but if I go this way, that would correspond to y equals -1, right? Because I'm measuring positive downward, so negative's going upward. Okay. So my integral limits would be from -1 to 1. That's where my window lies in terms of y values of all of this multiplied together. And what I want to show you is actually very, very easy to evaluate this integral for a couple of reasons. If I factor out the 2 and the 62.4 and distribute my square root into the y plus 99 and break this up into two integrals, the first integral is the integral from -1 to +1 of y times the square root of 1 minus y squared dy. And if you were paying attention at the beginning of the quarter, when you talked about odd and even functions, this is one huge advantage. I could do a u substitution. I absolutely could evaluate this with a u sub. But if you spot it as an odd function, which it is, remember that an odd function integrated from the negative to the positive of the same number will always come out to be 0. So if you spot that, that part would just be 0 and you could move on. The second part, I took out the 99, the integral from -1 to 1 of just the square root of 1 minus y squared. This represents, we saw this on a previous problem, that's the top half, or the, you could, if it's x equals, I guess you could think of it as the right half, but either case, it's half of a circle with a radius of 1. So if we're integrating from -1 to +1, it's just a half of a circle, which would be 1/2 pi times 1 squared, which gives me pi over 2. If I put that all together and multiplied 62.4 times 2, got 124.8 times this one's 0. This comes out to be 99 times pi over 2. And if you plug that in a calculator, this is maybe a little shocking. Just on that one little window that had a radius of 1 foot, there is 19,408 pounds of force acting on that window. That is a strong force. As you might suspect, when they build windows on submarines, they build them very strong. They have to withhold quite a bit of force as they dive under the ocean.